Hi everyone, how's it going? Today we'll be going over deriving moment inertia with the pivot point in the middle of a uniform metal rod. We'll also adjust the pivot point a little bit off center and we'll see how that impacts our moment of inertia. We'll also go through the derivation of a disk and a solid cylinder, and at the end we'll do a certain problem where we'll have to deal with these with moment inertia inside rotational kinematics. So without further ado, let's get started. So, let's have a rod of length 2L, or of length L, sorry, and we'll just place a pivot in the middle, at L over 2. So, how we're going to go about this is we have I is equal to the integral. So we're going to add up every single different piece of moment of inertia. So integral over di, which is equal to r squared dm, right? Whenever you find yourself in a pinch with moment of inertia, always go back to this simple principle, always. So from here, what we're going to do is we're going to need to integrate this over all these different radii. But to do that, we need this quantity right here to be dr, not dm, so we can integrate over r. Therefore, we're going to use a few properties. We're going to look at the linear density. So by looking at this linear density, we're going to look at the mass over the length, right? We're looking at one dimension. So if you want to find the density of an object in one dimension, we're going to take all the mass of that object and we're going to divide it by, well, its length. M over L, which is also equal to, and then we're going to go dm over dr. From here, we have an expression of dm in terms of dr. So what we can do is we'll have dm is equal to m over L dr. And right away, we can plug that in. R squared, and then we'll have ml times dr. And you can throw in our bounds. So because our pivot point is in the middle, we're going to want to encompass all of this region and all of this. So we're going to go from negative L over 2 to positive L over 2 to cover the whole area L. Now from here, what we're going to do is we'll just plug everything in and derive, at this point it's just a math problem, right? So what we're going to do is we're going to pull out m over L because they're both constants that do not vary, m over L, and we're going to integrate. So we're going to have 1/3 r cubed, integrate from negative L over 2 to L over 2. We'll have L cubed over 8 times 3 is 24. And then we'll go minus, or with the double minus right here, so we'll go to the plus L cubed over 24. This will lead to ml squared, because we have L down the bottom, over, we'll have 2 from adding those two factors together. 2 over 24 cancels out to 12. Therefore, we will end up as that for our moment of inertia about the rod above the center, if we have a pivot in the middle of that rod. So now what we're going to do is we're going to take the same rod, but we're going to move the pivot around. So instead of, we're going to have the same rod of length L and mass M, but instead of having the pivot at L over 2, we're going to have the pivot over here at L over 6. So it's L over 6 inside of the left end of the rod. So this might seem a little intimidating at first, but it's really just the same process, right? We're going to have I equals we're going to integrate over di is equal to, and we're going to integrate r squared dm, just as we did before. So that's our first step. Always start up with that step. From here, we could have the same argument for linear density, right? Because nothing's changed. We still have the same amount of mass or the same amount of length, and we can simply reduce it to dm over dr, and we will obtain the exact same conversion factor between dm and dr than we did previously. So from here, we could throw these in. M over L doesn't vary over this length. They're absolute quantities. they're constants in this case, right? So we could pull them outside of the integration, and we'll be left with integral and then r squared dr. Now from here, what we're going to do, this is the biggest change from the last problem, is that because we're no longer looking at the middle, we're going to have to change our bounds. We're looking at, if you assume that this is our 0 point, we're going backwards 1 over 6, and going that way 5 over 6, right? So our bounds are not going to be from negative 1/2 to 1/2. Now they're going to be from negative 1/6, or L over 6, negative L over 6 to 5L over 6. And so from here, as usual, we can, well, now it just becomes a math problem about how, how well you can integrate. And let's do that real quick. And I'll leave you to check my work, but this should come out to 7 over 36 ml squared. Another way we might take this problem and skip many of these steps is to use what we like to call the parallel axis theorem. Which states that the moment of inertia of, well, this problem right here would be equal to mr parallel squared plus I center of mass squared, but with the I center of mass. Well, we know what I of the center of mass is. Moment of inertia about the center of mass, which is right here, which we calculated. So we just do plus 112 L squared. But then we have m, but then this part right here might be a little confusing. R parallel essentially means the distance off of our center, right? So what is this would be R parallel, the difference between the pivot point and the center of mass. And so what we can do here is that because the difference between the two of them in this case would be 1/3, mr parallel would be ml squared over 9. And through some annoying fraction calculations, etc., this will come out to be 7 over 36 ml squared. This is best to use when you already know what the moment of inertia is for the center mass of the object. Sometimes, for better parts, sometimes you must have these memorized. It helps a lot when you're going through derivations for the other objects such as disks and cylinders. But this is always a handy way to do it if you're pressed for time, or if you want to approach this problem a little simpler. So next, let's look at how to derive the moment of inertia of a disk. All right, now let's look at the area of the moment of inertia about the center of a solid disk. Now, this might be a little more intimidating at first because instead of dealing with a one-dimensional object such as a rod, we'll be looking at a two-dimensional object. So it would be kind of frustrating to see where you start, but as always, we gotta start somewhere. So I is equal to add up all the moments of inertia, integral r squared dm. That is always the basis of a moment of inertia problem. Always go back to stuff that you could tangibly write down when you're stuck on a problem. Always. Now, before when we were looking at the rod, we could basically write out that dm is equal to the linear density times dr. In this case, we're looking at area density, right? Instead of linear density, we're going to look at the density over an area of this solid disk. So we're going to have sigma to represent that, but in this case, we'll have dm, sigma dA, over that area. Now, let's ask ourselves, so sigma is pretty straightforward. It's mass over the area, so it's pi r squared. But dA might be a little more difficult to understand. dA is, we're going to look at, dA asks us what areas are we going to add up to find the total moment of inertia of this disk. The way I would look at this is you have a disk, and if you look at it as made up as infinitesimally small, thin circles, if you take those circumferences and add them all up, that will give us the total dA of this disk. To make it a little more tangible, it might seem counterintuitive, but let's look at it in 3D. If you have a sphere, it might be a little more advantageous to look at it as the area of the whole thing as adding up infinitesimally small, thin shells of that sphere from 0 to whatever the radius is. So that's exactly what we're going to be doing, but in 2D, right? So dA in this case, so we're adding up infinitesimally small shells, is going to be 2 pi r dr. All right, let's with this and this, well, we can find dm. With a few calculations, we could cancel out the pi's, and then we plug it all back in, we're going to have m over r squared integral of, sorry, 2 should be outside. And now is the question, what do we do with our bounds? Our bounds is, as I explained before, we're going to be adding up infinitesimally thin shells of a circle, right? So we're going to be looking at the circumferences. And to find, we're going to start at 0, right? And we go radially outwards until we hit that final area, which is going to be r in this case, right? So we're going to go from 0 to r, and that's going to be our bounds for integration. Now it just becomes a math problem, and this first part, is always what is the most complicated part of setting up a moment of inertia problem. So let's go ahead and solve it. So 2m r squared, we're going to, and then bounds of integration, we're going to have 1/4 r to the 4th from 0 to r. 1/4 is going to cancel out with the 2 up top, so we're going to have m over 2. We're going to have r 0. When we plug in 0, it's not going to do anything, so we're only look at the first term. We're going to have r to the 4th. We'll have r squared cancel on the bottom, and we'll end up with is 1/2 m r squared. And yeah, so the main part whenever you tackle a moment of inertia problem is to look at how you're going to divide it up. In this case, I used the circumferences of infinitesimally small, thin circles, much as you would use for a rod. In a rod, you're looking at infinitesimally small, different DMs, essentially, is what you're looking at, to finally calculate it. In this case, we use circles, because it's a disk. Now, it might get a little more tricky when we're looking at a 3D object, a solid cylinder. So let's get into that. Now, when tackling a solid cylinder, it is a little bit harder, because when you start, I equals integrate di, well, how am I going to be looking at the cylinder? As I mentioned before, with the line, you're looking at thin dm, little infinitesimally small points of mass, certain r away from your pivot point, and that's how we find our linear density, etc. For a disk, we look at the circumferences of infinitesimally thin circles, and we add those up. In this case, this is where you can kind of be creative, because there are a lot of different ways to look at this. How you might look at it as very thin cylinders that you might want to add up from 0 to r. We're going to choose a different way. I'm going to choose a way where we'll look at it as infinitesimally thin disks, and we're going to integrate over height. So when asking yourself this, instead of integral r squared dm, because I'm looking at disks, I have to adjust right here. I have to adjust it to 1/2. Because, as we calculated before, the moment of inertia of a disk, which is what I'm basing this whole thing around, is 1/2 m r squared, as we just derived. Alright, so, with that out of the way, we could start making our density, or quote-unquote density arguments. So before it was linear density for a one-dimensional object, then it was area density for a disk, now it's going to be volume density. While looking at this density, we'll have dm is equal to, we're going to call this this density rho, as some of us might be familiar with, dv. This is where the fun begins, and let's get started. So we're looking for rho. Well, rho should be fairly obvious. We'll have a mass, right? Because we'll have mass of the whole cylinder over the area of the whole cylinder, which is going to be pi r squared, which is the area of a disk, times the height. Now, when we're looking at dV, this is when things might get a little bit more interesting. When looking at dV, since we're looking at it in terms of a ton of different disks of varying heights, not of varying width, radius, sorry. This is going to be pi r squared, right? Because it's going to be, or should remain the same. The radius is going to be the same for all disks, but we're going to integrate over the height, so dh. Notice in this case that the r right here is not going to be our variable. In this case, h is going to be a variable since we're integrating over the height and not over the radius. So what does that give? Plug everything back in. Well, before I plug everything back in, let's write it out and clean it up a little bit. So pi r squared all cancels out, and we should be left with m over h dh. So when we throw back in, we'll have 1/2 integral of from 0 to h, as we said before, we're going to integrate over the height. We'll have r squared. R squared is a constant in this case, not a variable, so we should make it capital. M over h dh. I included the m over h in the parentheses in this case because I just want to make clear that when this h comes from our density, which calculates over the whole area. So this h is always being integrated. This h is a constant in this case, which is a whole height. So what we're going to end up with is, well, since all these are constants, we're going to move them all out, and we'll have r squared m over 2h integral 0 to h dh. Now, well, this is just an empty integral essentially, where you just have one constant, and you'll have r squared m dh h, and we'll have 1 over 2 m r squared. It is important to note that in this case, we could have saved ourselves all this trouble if you'd done one very simple thing. When you're looking at moment of inertia, is how hard something is to rotate. Its reluctance to be in motion when it rotates. So when you're looking at a disk, and you're looking in the middle, the amount of particles of dMs of infinitesimally small masses that we're looking at away from the center, well, the cylinder is going to be the exact same thing, just a little bit elongated. So it makes sense that because we have basically the same, we'll have the same amount of mass that's even as distributed one as the other. Well, the moment of inertia is not going to change between the one and the two. So moment of inertia for the disk is going to have mr squared. And reasonably, because the mass is evenly distributed among the cylinder as it is among the sphere, well, inertia won't change, which is what we just figured out. So there might be a few moving parts in this problem, and always remember that you can pause on the video anytime and try to attempt it yourself. But let's start to explain this problem. We have a hollow hoop of mass m and of radius r. Given that the moment of inertia of a hollow hoop is equal to mr squared, that you could derive yourself, or you could figure out intuitively. We were told to find the moment of inertia of a rod of about the center, which is probably about the center of a rod that is 2r length and n with the mass n. Finally, in the second part of the problem, we'll have the rod inside of this hoop, and we'll have it roll up a slope at an initial angular velocity omega naught, and we are told to find the angular acceleration due to the forces using Newton's second law. Finally, we'll have to find at what time does the hoop stop due to this angular acceleration. So without further ado, let's derive the moment of inertia of this rod. Start with the basics. I'll go a little bit quicker through this one since we've done it twice before. Always start with our initial argument of r squared dm. dm is equal to linear density times dr. Linear density in this case is going to be m over 2r. dr dm. Now, for sake of symmetry, because this rod is uniform, what we can do in this case is we can integrate from 0 to r instead of from negative r to r with times 2 to the outside. So when we plug it back in, this 2 and that 2 cancels out, and you'll be left with m over r squared dr. Going through the derivation, we'll have m over 3r times r cubed, which we will end up with that expression for the moment of inertia of a rod about its center. Now for B, this requires a little more algebraic prowess, I guess. So let's redraw the diagram. Inertial theta. And we'll put this hoop and rod system together. And in this case, we'll be rolling it up at a certain initial velocity, but since we're looking for angular acceleration, this doesn't really factor in. Let's start off with our Newton's arguments of torque. And alpha is what we're looking for. Now, this moment of inertia might be a little tricky at first, but moment of inertia is additive. So we're going to take the moment of inertia of the hoop, we're going to add it to the moment of inertia of this rod, which will be equal to our alpha, which is in turn equal to the forces acting upon this object. There will be a friction on the slope, and we'll go about it by writing it as we have a gravitational force going downwards. I'm going to kind of skip over this part. Let me know if you want a more in-depth view of mass on slopes, but we're going to look at the component of the gravitational force along the slope, and we shall have sine theta 2mg because the cumulative mass of both of the system, and then, well, that's the 2mg. It would be the gravitational force, and sine theta would be the direction of our slope. And then from there, we'll have our frictional force. Frictional force will do torque on the object, a radius away, r. Now, we're kind of limited because we have two parts we're trying to find, and only one equation. So this is when you can bring in good old linear. And so, much like we did with moment of inertia, masses add, as we deduced right here. So we'll have 2m times a is equal to, well, we have the same forces, right? We still have the gravitational force, and we still have the frictional force. So in this case, we'll have 2mg sine theta, as it is, there should be an r here, my bad. I miswrote in the beginning. There should be a lever arm for the torque upon the object, which is my bad. Forgot to mention that. But essentially these two terms are going to be very, very, very similar, except for that that torque lever arm. And in this case, we'll have those two equations. Now, from these two equations, we can just solve for this one and plug it back into this one, which will give us the frictional force will be equal to -2 ma minus 2 mg sine theta. From here, we're going to plug it back in, and take note that linear acceleration is equal to r alpha. Once again, we could derive that from the arc length equation. If we integrate both sides, we'll have the integral over time of theta, which will be omega. R is constant, and the integral for the length will be v linear. And from there, you take one more integral and you arrive at this equation right here. So by plugging everything back in, including the moment of inertia, it shall give us a pretty ugly expression that will give us the answer. Now, although this is very ugly, we can simplify a good amount of it. For example, common terms, and then this part is we can simplify a lot. Since we have an r that we can factor out from both expressions here, we can take away an r squared on this side, which will leave us with r alpha minus 2g. We can also notice that in this case, every term in this expression has an m, which we can cancel out as well. And we could, because of this m, these two terms will be identical, and we can add this term to both sides, which will give us Alright, and from here we have a simple last algebraic manipulation to give us our final answer for the angular acceleration, alpha. Now let's write up to this side right here, part C. Well, for part C, we have a constant acceleration. So we have constant angular acceleration, we know alpha, and we know omega naught. We're given omega naught, and we're looking for how much time it'll take to come to a stop. So omega final be equal to 0, and this is the expression we just found. -3g sine theta over 5r. All we're looking for in this case is time. And so, well, we have a kinematic equation for that. Plugging everything back in, we'll have 0 equals omega naught minus 3g sine theta over 5rt. T will end up being 5r omega naught over 3g sine theta. And that should be it for moment inertia. Moment inertia is a concept that can seem very scary at first, but after working with it a good amount of times, that fear will slowly subside into a slight weariness and a slight cautiousness when you approach the subject. I hope this all made sense. Please let me know down in the comments below if there's anything else that you guys might want to see on mobile inertia. And I hope you have a great day.